Today, the ds-incubator continues on the series about building shiny apps, and we're going to be covering today a couple of topics that we didn't have time to cover last time. It is still within the big topic of reactive expressions and reactivity, but we did not talk about the reactive graph, which is important because it helps us understand how the inputs and outputs connect in an app. So the focus of today is precisely to understand how inputs and outputs are connected using a reactive graph as a tool to understand that. Also to learn how to build that reactive graph with a package called React Log, which does that for us, and explore briefly an example that Hadley presents in the book, Mastering Shiny. Explore that example to understand why reactive expressions are very important. This is following up from the series, so if you haven't been in these meetups before, you will feel very lost, I think. And this is also kind of probably one of the last meetups where we talk about theoretical ideas, and hopefully we'll start soon showing more fun stuff. But let's start with this little shiny app that you, if you were here, you should probably be familiar with. It is a very small app that has two components, an input where the user inputs the name, and an output that the application gives a greeting. So basically we have these two things, a name as an input and the output is a greeting, and we connect them here. The server function is the one that connects inputs and outputs. So basically what we do is we paste the string hello with the name that the user gave in the input, and we assign that to the greeting output so that it's shown on the app. So let's see what the app looks like. Here it is. So if I say Mauro, I give my name, and there we go. So the application greets me as hello Mauro. So one input, one output. And what we're going to be talking about now with this app as an example is how we can think about the connection between that input and that output using this tool called the reactive graph. There is this little sketch here where I have the input name that has an arrow that points to the right, and then we have this greeting that represents the output that has this other symbol that kind of the input fits in the output. So that is the basic idea of how to represent inputs and outputs and the connections between them using the reactive graph. But that's not very fancy. Let me show you something a bit more exciting. For that, we're going to be using the package React Log, which if you don't have it, you'll need to install. And all you need to do is to run the function React Log enable, and that will allow you to do I have the app running here in the background? Yes. So if you have the app running, you can press Ctrl and F3, and that will pop up this new window that shows the elements of your app and their connections. So here on the right, you see output $greeting, so the output that we defined, and on the left we see input $name. So the connection between them is represented by this arrow. This is trivial, of course, but soon we're going to be seeing a more complex app, and the reactive graph will help us understand which parts of the app will recompute when some input changes and which parts of the app will not recompute, so that we save computation time. So let me rewind, because one really nice feature of this tool is that you can see how the app progresses since the app is initialized. So the app starts, the server function creates this instance for the user that is using the app. And what is the state? Well, the state is that the inputs are already defined. This is something that I'm not sure if it's like a glitch or what, but usually I was expecting the inputs to be colored in green because they are already defined, they're already ready to go. And that's how Hadley represents them in his book. So I don't know exactly why they are colored in white here. But so the first stage is, the inputs are defined, but then nothing else is, being computed, or nothing else is happening really in the app. Then the next step is that Shiny picks any output. We can think of it as picking it randomly. It looks like there is something to it, but Hadley talks about the selection of the first output randomly. In this super simple app, we have only one output, so it is the only one that can be chosen. But if there were many, one output, anyone would be selected. And then in the server function, there is a definition about which input relates to that output, right? Or which, we're going to see soon, which reactive expression is needed to compute that output. So the output is something that we need to compute, but now it is being calculated, and the server function tells Shiny that the output cannot be calculated unless we get the input. So if I click here and advance the app, what happens is that input, and now that's color green, but that input now has a connection to that output. So let's go one step below. So this arrow did not exist until the output needed to be calculated, and only then is when the server function tells Shiny, okay, what you need is input name. Then this connection is created, and it is also cached, so that now Shiny knows that is the thing that the only thing that needs to change in the case of this application. If that input changes, then the output will change. But if that input does not change, then nothing needs to be recomputed, right? And that's one of the beautiful things that the reactive paradigm has, that laziness that saves computation time. So let's advance the application. So now the input is available, but it hasn't been still used. So if we advance the app, now that output has used the input, has made the calculations that the application defined, and now we have like a fully fledged application. So I'm going to click forward, but I expect nothing else to change. Okay, so here it looks like what is showing is the stage where I add my name, so it's showing the whole session of the application. I think I then corrected my name with Mauro, and then you can see how this is moving. So basically it's repeating the loop from everything in the initial state to a fully fledged application, and then when I change the input, then the output gets invalidated and is again recomputed with a new input. Okay, so that was a little bit of a overview of the reactive graph. Let's close this up for now and move on to a little more complex application to see how the graph looks like now. So let's move on to, I already have defined the UI above. I'm going to be using the same UI, but now the server has a little bit of a difference. Let me show you both servers so you can see. So notice how the line that calls paste, line 14 here, is directly in the render text function. And now here in line 26, the variation that I'm presenting now is one in which instead of calling paste directly on the render text function, I extract it into a reactive. In this particular application, this is not necessary at all, but it is just for demonstration purposes. So what I want to show now is that between the input and the output, we now have this new node that is created by a reactive expression. And when the application is trivial like this one, it is an overkill, absolutely. But when the application is bigger, having those intermediate nodes does help save computation time. And I'll show that in a more complex example after this one. So let me then run a server here and show as an anticipation of what you're gonna see. here is my manually developed reactive graph. So what we expect to see is an input to the left that connects to no longer directly to the output, but instead to an intermediate reactive expression that has properties of both inputs and outputs, because notice how it can fit the input on the left and also it can be fitted into the output to the right. I hear some noises. Do we have any questions here or comments?
Sorry, I was on mute.
Oh, no problems. In any case, in a few minutes, we're gonna get to the comments section. So the way you read this relationship between inputs and outputs, let's start here at the top, is simpler. The reactive graph that you saw first is telling us is that greeting will need to be recomputed whenever the input name is changed. And the way to express that in Shiny jargon could be as follows. Could be greeting has a reactive dependency on name. So translating that to this new reactive graph where there is an intermediate string, the way I think I would phrase it then is that greeting has a reactive dependency on string, and then string has a reactive dependency on name. So let's see what that app looks like, and let's run the reactive graph. So I'm running now the new server, predefining server, running the app. Now I need to find it here in the background. Here it is. And to use the React log package, again, what I do is I press Ctrl F3. And here I have it on the back end. And here it is. So before we have this only 2 nodes, and now we have 3. We have this one in the middle. I'm not very sure what this theme here actually means. And one thing that that you might notice is that the names output greeting and the name input name are kind of nice names and meaningful, but then that the reactive expression does not have a name, does not have a beautiful label. Instead, it has just the code. So that is hard to read, and we can improve it. And the way we can improve it is by, let me stop the app. The way we can improve it is by using an argument that the reactive function has that is called label. Label, there you go. And we can call it string. So now the reactive graph should be a little nicer and more closely reflect the application that we have here, more closely reflect the names that we are using in the server function. So here is the app. It behaves just as the other ones that we saw before, but the underlying graph is different. So let's see what it looks like. And here it is. So we have our output to the right, our input to the left, and in the middle we have this reactive expression, right? Which is just code that has been extracted outside of the render text call. So now it is time to actually demonstrate why this is important, because so far this is just an overkill, as we don't really need this reactive, this string reactive here. But to show that in a more meaningful way, we need a way more complex app. So instead of confusing you with code that I already copied from the book, what I'm gonna do is directly show you the app from Hadley's book. Here. There you go. So the app we're gonna be working with now is this one here. It's still refreshing. There you go. So what you see here are 2 distributions. Here on the left, distribution 1, in the middle, distribution 2. The 2 distributions have parameters, 1,000, but we can change that, let's say 500 here to the left, and we leave 1,000 to the other one. And then we can compare how the 2 distributions vary using 2 summaries. One visual summary, that is this plot that you see here, from which, of which we can also tweak a little bit with some parameters here, like the bandwidth, for example. We could do it 0.2, for example. And then we also see this summary in the form of a p-value, basically comparing these two distributions analytically, right? So the underlying code is not important. What is important is the underlying graph. So that is exactly what I want to show you. And before I show you that, let's analyze a little bit this snippet that does come from that app. So, for example, to calculate that t-test that I showed in the app, what it does is first it computes a value x1 based on a random pool of values that depend on the inputs that the user gives, and the same thing for x2. And then it uses those values to compute the t-test and to see if those two distributions are significantly different or not. But for you as a human, you would know that, okay, if I change, say, n1 only, which was, remember, n1 is this parameter here, right? You would expect only to recompute x1. You would expect not to need to recompute x2. However, depending on how you craft your app, that might not be the case. So Shiny is not clever enough to know which sub-piece of an output needs to be recomputed. And instead, if any input changes in an output, the whole output will change. So let me show you the underlying code of the app. And here it is. So for the t-test, for example, notice how the output t-test, the one that will eventually be shown in the app in that little square to the right. So in order to see these numbers here, right, what we have is this underlying code. We are defining t-test there. And notice how both x1 and x2 are with... Say again?
20 minutes now.
Thanks a lot. So we should be wrapping up now. So notice how both x1 and x2, both of them are defined inside the call that is assigned to output. So Shiny will detect that x1 changes and will recompute both x1 and x2 because both of them are inside this output. So Shiny, again, and last time I said, recomputes everything within one output. So the solution to this problem, if you want to save computations and ask Shiny to only compute or recompute only the outputs that depend on the specific inputs that change and not in others, then the solution is to extract this code outside of the output as a reactive. So this is what Hadley does here soon. But before I show you the result, let me show you this underlying graph. So the application, as I showed it before, produces this very complex graph where pretty much every input, N1, min1, and SD1 are connected to every output. Also, if you look how, for example, t-test will change when N1 changes, but it also will change when N2 changes, and so on and so forth. So if you follow these lines, you will see that this application is very inefficient in that it will be recomputed just about every time the user tweaks any control. So the solution for that is reactive expressions. So now look how this code changed. Notice how the definition of x1 and x2 no longer is inside the calls that are assigned to the outputs, but instead are outside the outputs, inside the server function, but outside the outputs, right? And then we can use x1 as you would normally do with every reactive expression, where you call them as if they were a function, right? So x1 is used here and x1 is used here, but if only, for example, n1 changes, then only x1 will recompute it, but not x2. So now if I show you the graph of this app, it looks a lot cleaner. Now, t-test has a dependency, a reactive dependency on x1 and on x2, but in turn, x1 has only a dependency on everything that relates to the one inputs, right? And one mean one and SD1, and not a dependency on everything that is related to the two inputs, right? So notice how this small change, this small refactoring in the server function has a huge impact on what is computed when the users play with the app. And this is a point that Alex did 1 or 2 meetups ago, and hopefully now we have a more visual grasp of the meaning of that comment. I think now is a pretty good place to stop for questions and comments, because the only thing I have on the list here is to show basically the steps that the app does from being totally fresh to being fully fledged, but we already kind of walked through that. So I stop here and ask, do we have questions or comments? No, okay. Maybe I'm gonna do a little bit of the briefing, like a summary of, I would like to kind of to phrase the takeaway of this. So we've been covering reactive expressions and the server function in general. The reactive graph allows us to understand how inputs and outputs are connected. The connection is defined in the server function, but the reactive graph allows us to understand those connections, and maybe by visually exploring those connections, realize how our app should be refactored. So if we do see a very complex graph, it might be a sign that there might be a better way to write that code, to refactor that code, to minimize the number of unnecessary computations. So you would like the app to compute only things that need to be computed, to be as lazy as possible, so that the time that the user spends waiting for their application to react is the minimum. I acknowledge that the reactive paradigm of programming is new to most of us. It's very different to the imperative programming paradigm that we are more used to when we write scripts, and therefore in the beginning it takes a while to grasp. And with these meetups, I'm not hoping that you would have fully understood reactivity or reactive expressions, but at least know that they might be useful, particularly if you find that your app is laggy, is slow. You might need to think about how to use cleverly reactive expressions to avoid recomputing things that don't necessarily need to be recomputed. That is about the end. Do we have any final thoughts or comments?
I guess I have one, which is having stuff be reactive is very cool and makes your dashboard look very neat and slick. But if your computations are inherently slow and, for some reason it's like you're moving around a lot of data and no amount of optimizing your reactive graph is going to help the function run faster, consider using not reactive components, because it's one of those things where if a process is inherently slow, letting the user feel like they have control over when it runs is better than if it keeps trying to update as they change things, and then it just feels slow. It's one of those counterintuitive user experience outcomes that even if the entire process takes longer, it doesn't feel as slow for them.
Interesting. Here I take totally your word because my experience using Shiny, building Shiny apps is minimal. So this is more like a theoretical. But what I understand from reading is that so if I'm using, say that I need to compute some kind of data, and I have a data set, I need to do computations and get like an analysis, or intermediate data set, right? That results from computation. My understanding is that if I wrap that in a reactive, that will be recomputed only when it needs to, and not just randomly. Did I get anything kind of wrong there? What do you think is going on?
So that you're spot on there. I guess my point of caution here is like, say you had a function that takes, I don't know, even 200 milliseconds to compute, right? That is pretty commonly accepted as what humans can perceive as instantaneous. So if you have a function that takes 300 milliseconds to compute and it's trying to recompute on every keystroke, then the application is just going to feel slow, right? And sometimes there's no way to get around writing a function that's going to take 300 milliseconds because it has to like process data frames and stuff.
Yeah.
So that is my point of caution here. Like, there is a lot of stuff that is lightning fast and can easily come in under that time threshold. But for anything where you're moving around a lot of data or doing any heavy lifting, consider having that be a button, not a reactive.
Yeah, that's great. I think that reminds me of something I chose to exclude because of time constraint. But probably the motivated reader could go to this section called controlling timing of evaluation, and I think it totally taps on what you, Alex, are saying, and offers some approaches to that. So basically, for example, what you can do is add a click button that say, okay, now compute, right? So instead of the thing being computed as the user changes something, they are free to change everything, and then when they're ready, they click a button one time, and then all of the settings that they have changed kind of get applied and get computed. So there are a couple of strategies, very, very clever, that it looks like are very connected to what you have just said, Alex. I'm sorry that didn't make it to this meetup. Okay, thanks a lot for joining today. See you next time.
Ciao.
Ciao, ciao.